Hello, everyone. Today I'm going to talk about the composition of machine learning interatomic potentials in Julia. This work is part of the SESMIX project that seeks to advance the state of the art in predictive simulations, connecting the quantum world and the machine learning world and the molecular dynamic world with the state of the art programming languages, compilers, HPC abstractions, and certain notification. So, thank you. In material science, there are problems that require a large amount of computations, like the hypersonic flows mentioned in the slide. This kind of simulation can take several months to complete, and within the simulations, the computation of the interatomic forces are a bottleneck. So accelerating force calculations is a must if we want to address large systems. We can use first principle physics to do this, but it's very expensive. So there are surrogate models that provide accurate and fast approximations to these force calculations. These are called interatomic potentials, or in the recent years, machine learning interatomic potentials. One way of describing these potentials is through these elements here. On the one hand, we have the data, and we are talking about the atoms' positions, the atoms' type, the geometrical parameters, the energy of each system, the forces associated to each atom. And this data will be used to fit the model. And on the other hand, we have the model itself that is composed by a set of descriptor functions that are based on the atomic configurations, and how we link these descriptors to compute the energy of a system, and through the energy, the forces. In the atomic cluster expansion, for example, a linear combination of these descriptors is used to compute the energy of a system, but also we can use another approaches, nonlinear approaches. We can use a feed-forward neural network, a graph neural network, etc. From all this complexity emerge a plethora of combinations between data, between descriptors, how we link those descriptors, the hyperparameters of the models, etc. And we are interested in finding these combinations that exceed the state of the art in terms of accuracy and performance. So we are developing software for facilitating this task, for automating this task, and at the end of the workflow, provide a model that can be used in Julia, but also in other platforms. Julia can help in this task in many ways, among them facilitating the development of software abstractions by providing automatic differentiation for the computation of the gradients, the computation of the forces, by providing the machine learning abstractions that we need to define those models, and the high performance abstractions that we need to define to accelerate the training and to compute the forces. Among the software abstractions that we are developing, we are trying to develop interfaces that simplifies this process of composing classical descriptors like the ones of the atomic cluster expansion with novel nonlinear formulations, from feed-forward neural network, very simple things, to more complex like graph neural networks. So the idea is to reduce the complexity of developing these potentials. I also mentioned that automatic differentiation is critical here, because every time we need to change a model, we need to compute the gradients of the model to compute the forces. So we need good tools for doing that. And Julia provides very interesting tools for that, like Zygote, like enzymes that are integrated to machine learning frameworks, also in Julia, like Flux or Lux. We need to be careful if we want to compute the energies, the gradients analytically, because sometimes using automatic differentiation can meet or exceed the performance of analytical versions. And by the way, computing analytical solutions of these gradients is not an option here. when you need to change the model, it's impossible in terms of productivity, calculate the gradients each time you need to evaluate a new model. We are developing these workflows that allow us to define these potentials, define the parameters of the descriptors that we are going to use, compute these descriptors based on the input data, define the model that we are going to use, the neural network model here, define the loss function, and then perform the training in an easy manner. One focus of this work is reduce the complexity for that. We have also another version with GNS convolutional neural networks using graph neural networks, JL, that we are experimenting with. The next level is to automate this process. And here we are defining the space of different combinations. We want to define the hyperparameters of, in this case, A's. We want to know which values can take the body order, the polynomial degree, the cutoff radius. We want to define which models are we going to evaluate, how many epochs, the size of the batches, which optimizer are we going to use. And if we are going to perform data transformations, if we're going to reduce the redundancy of the data set, which algorithm we are going to use. If we are going to generate more data, which algorithm we are going to use. If we are going to use different optimization solvers, like random sample, Bayesian optimization solvers, which are those solvers. And after that, many experiments will be executed in parallel. And at the end of the experimentation, we will decide which is the best experiment based on the accuracy that was provided and based on the performance of the interatomic forces calculations. We hope this work help us accelerate the development in material science by providing new, optimal, interesting, fast, and accurate potentials. Thank you.
Okay.